Okay, we will see some important points in the class 12 max chapter 5 continuity and differentiability. Okay, now let us take a function. This is the definition of the function f of x is equal to 1 for x is less than or equal to 0. 2x is greater than 0. Okay, so now the left side it covers 0 also, less than or equal to 0. Okay, this less than or equal to 0, but this on the right hand side we don't define the value of the 0. X is greater than 0 is 2. Okay, greater than 0, so there is a hole here, that is undefined value here at x equal to 0 on the right side. Okay, see new how to find the LHS and RHS limits. So there is a reference video attached in the description, you can go through it. It's a 5-minute video only. Okay, so now at this x equal to 0, if you draw like this, then you have to take out the bend because there is a discontinuity here. Okay, you cannot draw this smooth. Okay, so left right side mismatch at x equal to 0. Okay, so now if you go through the function, of course define and here. Okay, so now this function is so now when you draw, note that when you draw the graph, we cannot draw it at one stroke without lifting the pen on the from the plane. Okay, let's see at x equal to 0, because there is a abrupt transition here, it is not defined here. It is greater than 0 only is 2, not at the 0 on the right side. So this is one is a function being not continuous at x equal to 0, because it is transitioning from 1 to true. It is not continuous at x equal to 0. This is function is not continuous at x equal to 0. Now you take this example. Here this value for this function is 1. X is not equal to 0. Okay, equal to 1. Okay, this side also 1, this side also 1. So it is not defined at x equal to 0 and 2 at x equal to 0. Okay, here also there is a abrupt transition. Without lifting the pen we cannot draw the graph. Okay, not coincide the function without lifting the pen. Okay, cannot draw the graph of the function. This is yet another instance of the function being not continuous at x equal to 0. But although these LHS RHS is same, but at x equal to 0 they are not coincide. Value of the function at is 0 equal to that does not coincide with the common value of the left and right side limits. Okay, this is important. Okay, this is definition one. F of x is a real function on a subset of real number. Let C be the point on the domain, then the f is continuous at C. Okay, these are the conditions. Okay, now to check the continuity, this is a point and of the function C is the point. To check the continuity, this is the rule. Okay, rule, a function is continuous at x equal to C. This is the point. Okay, if the function is defined, okay, at x equal to C, function should be, first of all it should be defined at that point. Okay, and if the value of the function is equal to the limit of the, so then it should be defined and LHS and RHS limit should match. Okay, so here at x equal 1 it will be 5. So this limit and the function value matches, so it is continuous at x equal to 1 at this point. Okay, it is continuous, it is defined and also it is matching this which value. Okay, so here this also f is continuous at x equal to 0. This is 0, this is 0. So here you should know what is this modulus of x, how to define this modulus. So this is how you define this modulus function. Minus x is less than 0, then x is greater than 0. Okay. So now greater than or equal to 0. And left hand limit, right hand limit, and the value of the function coordinate, hence f is continuous, is okay. The is matching, okay. At x equal to 0 they are asking, okay. So this is these two RHS LHS limits are matching, so it is continuous at x equal to 0. See, this is x is not equal to 0 and x equal to 0, it should be 1. Now if you put x equal to 0 in this function, then you will get 3 here, okay. So these two won't match, it's not continuous at so we have to show that function f of is given by is not continuous at x equal to 0, because is defined x is 1, but as per this it will be at 0 it will be, the value will be 3 as per this. So they are not matching. The function is defined as x equal to 0 and its value at x equal to 0 is 1. That is the definition, okay. It is definition. But when x is not equal to 0, the function given, okay, when this limit, if you make x tend to 0 based on using that function, that value will be 3, okay. This limit and the defined value is not matching, okay. This is a limit. If you x tend to 0, if you put x equal to 0, you will get 3. So that limit and the defined value is not matching. So that is not continuous at the point, okay. Note that f at x equal to 0 does not coincide with f of 0. The function is not continuous at x equal to 0, okay. We are asking is not continuous at x equal to 0. So it is not continuous at x equal to 0. It is the only point of discontinuity of this function. K is continuous, K is a single value, constant value. So you can go through it. So f is continuous, the real number. So this is the definition. A real function f is said to be continuous if it continues at every point on the domain of f. Okay, every point on the domain of f. Okay, this is a plus and this is the b minus. These are the limits, a plus b minus. Observe that f isn't a, f and b, f do not make sense, as the consequence of this f is defined only at one point. It is the continuous there, that is if the domain f is a singleton, f is continuous function. This is a notation, okay, limit notation. Is the function defined by f of x, x is a continuous function. We say that f, okay, this is the definition, greater than or equal to 0. Okay, is continuous for all positive elements, f is continuous all the way. We can go through it. Discuss the continuity of the function f of x equal to 1 by x. X is not equal to 0, that is important. What happens if you put x equal to 0, 1 by 0, then it will become infinity. That is not the real number, okay. Infinity is not the real number. So x is, the function is not defined at x equal to 0, so we should not worry about the function value at x equal to 0. That is defined for x is not equal to 0. Any non-zero real number we have, Okay, real number c, we have the limit, okay, 1 by c. Also, since c is not equal to 0, 1 by c equal to is f of s continuous at every point on the domain f is continuous function. We got 0, it is infinity, that is not idea, but that function is not defined for x equal to 0. That is important here. So we should not worry about at x equal to 0. Concept of the infinity. What do you understand the concept of the infinity? This is what did you analyze, okay? Positive infinity, okay? To be read as right hand limit of f of x at 0 is plus m infinity. Right hand limit, okay? We used to emphasize that plus infinity is not a real number, okay? Infinity is not a real number, and hence right hand limit of f at 0 does not exist in a real number, okay? Infinity is not a real number, okay? This is for the positive infinity, and this curve for the negative infinity, okay? It will go down. Again, negative is not a real number, and hence the left hand side does not exist for the does not exist as a real number, okay? Discuss the continuity function. X is less than or equal to 1. This is greater than 1, but at 1 this is defined and it is not defined. We have to use, see, less than or equal to 1. This is greater than 1. This function is not defined at x equal to 1. So now function is defined at all the points. If c is less than 1, then c plus 2. So it is c plus 2. It is continuous for all limit less than 1. Greater than 1, this is c minus 2. Okay, that is f is continuous or greater than 1. But at c equal to 1, the left side is 3, right side is negative 1. They are not matching, okay? Left side will be 3, right side negative, left hand mismatch. Since left and right hand limit at x equal do not coincide, f is not continuous at x equal to 1, okay? See here, this is not defined for x equal to 1. It is x greater than 1 only it is defined. Here x equal less than or equal to 1 including 1 it is defined. These two limits are not matching at x equal to 1. This is important. Okay, these limits. So we have to use this function to find the limits. This is important. So it is defined at all the points x plus 2 x. We have to find using this LHS RHS limit at x equal. This will be 3 and this will be minus 1. So they are not matching. Okay, since left and right at x equal do not coincide, not continued at x equal to 9. X is the only point of discontinuity. Discuss the continuity of the function. Okay, here at x equal to 0 they are not at all defined, so you don't have to worry. See, x is less than 0, x is greater than 0. Observe that a function is defined all remain except at 0 domain of the definition of, okay? So this domain 0 itself is not at all there in this domain. So here since 0 is not there, you don't have to worry about that value, okay? Although it is there is a discontinuity, it is not defined, you don't have to worry about that. Note that graph of the function, we need to lift the pen at 0 from the plane of the paper, but we need to do so that only for those points where the function is not defined. Okay, so it is a continuous function because the function itself is not defined at x equal to 0. Function not defined at so that is why f is continuous at all points of the domain. So that domain does not include 0. So here 0 they have defined here less than 0. Continuous. See, it is continuous, but at x equal to 0, these two are again 0. So, there is a continuous. Okay, LHS, these limits are matching, so it is a continuous function. Every polynomial is a continuous. So, you can go through this. This definition: find all the points in the discontinuity of the greatest integer function defined by this. Okay, this function, this graph. Okay, this definition of the function is this, so you can understand how they drawn this. Greatest integer less than or equal to x. Okay, at this x2 means, okay, greatest integer less than or equal to 2 is greatest integer is 1. Similarly for 4 it will be 3. Greatest integer less than or equal to the x. Every integral point. Okay, algebra of continuous functions. Those theorems you can go through it. This is the definition of the rational functions. Okay, p by q, p of x, where q of x is not equal to 0. Okay, continuity of the sine function. So this limit of the sine function at x equal to 0 is 0. Okay, so f of x equal to at point C, f of x is a continuous function. Sine function is a continuous function. Cosine function also similar. G is the subset of F, domain F. G is a subset of domain F. This is how we write this. Okay, you can try, at least you try these things. Differentiability. Recall the following facts from the previous class. Okay. The derivative of f of x is denoted by the f dash of x. This is how you denote, you indicate the derivative. F of x, this derivative is f dash of x. So d by df of f of x equal to f dash of x. The process of finding derivative of a function is called, this is the differentiation. We also use the phrase differentiate f of x with respect to x. Okay, this is differentiate f of x with respect to f, that is f dash of x, differentiation. These are the rules of the differentiation. Okay, u plus or minus v dash, that is derivative, u dash plus or minus v dash, product rule, quotient rule. So this is how x power n, nx power n minus 1. This is the derivative of x power n. Similarly for this sine, cosine, tan. So if limit this is does not exist, we say that f is not differentiable at C. See here this plus and minus here, domain differentiation on the left and right side. This is right and this is left side. Your function is said to be differentiable in the interval AB if it is differentiable at every point in the AB. Okay. This is theorem. If function is differentiable at a point C, then it is also continuous at this point. Okay. If a function is differentiable at a particular point C, means it is also continuous at that point. That is important theorem. Okay. So this corollary means this is other way. So here it is differentiable. That means it is continuous at that point. So every differentiable function is a continuous. Okay, based on this above statement. Okay, that is why it's a corollary. So it is left side, so negative here. Is right side positive. Right hand limit positive. Okay, here right side 1, left side negative 1, sudden jumps, not differentiable at f is not differentiable function. Okay, this limit does not exist, hence f is not differentiable at 0. Because at 0 it is sudden jump. Composite function. Okay, you can take this as a composite function. So you can expand this and find the f dash of x. Otherwise, you can assume t equal to this 2x plus 1 as g of x. Okay, then use the rule. Then after that again you put the t. Chain rule. So using the chain rule, you find the derivative of this function. Composed of two functions, indeed. One function is x square, other function is sine. Okay. So now v of t equals, we are putting x square equal to t. Okay, sine t. Then use that rule. Okay. Sin t is cos t, then 2x square is 2x. Then using that rule, then you apply that rule, so cos t into 2x. So now you replace the t, that is x square here. You can alternately, you can also directly do it, cos of x square into 2x. Okay. Similarly, you can find the derivative. Okay. So here we have three functions, sine, cos, then x square. You see how they are using. So you try, at least you try this, some of the things. Derivative of the implicit functions. Until now we have been differentiating various functions given in the form y equal to f of x. But it is not necessary these functions always expressed in this sum. For example, consider this. So from this you can find y from this equation, then substitute here. The first case we can solve for y and rewrite the relationship. Okay, then use it in the second case. Y is given as the explicit function. dy by dx, if okay. See, differentiate y with respect to x. Okay, dy by dx, here x is 1, this will be 0, constant. dy by dfx. Okay, so now this is 0, means these two are same. Okay, see, dy by dx plus d, this sign equal to this. Okay, now see here, this is, we are differentiating this with respect to x. There is a variable x here, but this is not here. So that is why dy by dx. Okay, then for the differentiating the sine y cos y, because there is no x here, we have to put again dy by dx, but on the right side we have x here, so minus sine x, we are not putting dy by dx here. Okay, that is important. For this term we are putting dy by dx here because it is x, with respect to x we are differentiating, that is not there here. That is why, but here x is there, so we are not putting dy by dx, additional dy by dx. Inverse dynamic functions. Okay, f of x is sine inverse of x. X equal to sine of y other side. Okay, y equal to sine inverse of x. When sine comes this side, the inverse will be cancelled out, other side. So here again you see differentiate with respect to x, we are adding dy by dx here. Exponential and logarithmic functions. So if you plot the curve for this function, as the power of x increases, the curve becomes steeper. Okay, steeper as the power increases. You will see this is steeper than this, and this is steeper than this. Okay, as the power of x increases, curve becomes steeper. Curves at steeper, the power x increases. Polynomial function is dependent on the degree of the polynomial function. Higher the degree, greater the growth. Definition: exponent is the positive again this function. Okay, these things you can go through it. The exponential function with a base 10 is called the common exponential function. Okay, with a base 10. Exponential function with base e is the natural exponential function. Base e natural, this is common. So here this definition, let b is greater than the real number, then we say logarithm of a with the base b is x. Okay, so here what is b x, we can take one example. Let us say base of 2 power 3 equal to 8. Okay, so now we can write that log of 8 with base 2 equal to 3. Okay, this without log. Okay, 2 power 3 equal to 8 without log, but if you write in terms of log, base is here 2, log 2 of a is 8 equal to, that is 3, that is x. Okay, so is 2 power 3 equal to 8. So here b equal to 2, x equal to 3, a equal to 8. Similarly for the other examples here. These are the graphs for the log functions. Natural logarithm is indicated by this ln. These are the various log formulas. Okay, should remember this. Log p equal to p plus q, log of p plus q, p power this is 2 log p. These formulas you should remember. This will be used in the following examples. So these theorems, okay, derivative of this e power x is e power x, log x is 1 by x. So chain rule is already defined. Logarithmic differentiation, you should be able to use those logarithmic formula here. Okay, this ux power this, so this power will come on the left side here, then log. Okay, log p square 2 log p, above we have seen like that. The above log formula we are using here. See here The square root is nothing but the power of half, the whole power half. Then you can apply that log formula, power formula, half log this a by b means a minus b. Okay, half log this whole thing is a top, okay, minus this b. Within this, then log ab equal to a plus b, okay, a plus b. So above you refer to the above log formulas for this. This half is nothing but the square power of. So these are also the formulas are given above, okay, all these formulas. Derivatives of functions in the parametric form. X equal to f of t, y equal to g of t is said to be parametric form with t. Okay, that is the parameter. T as a parameter. So how that is used here, you find the dy by dx of this x equal to this, y equal to this. The here t is the theta, okay. So now x equal to a cos theta, y equal to, so dx by d theta, okay, you differentiate this, dy by d theta, you differentiate this, then dy by dx equal to dy by d theta, dx by d theta. Here theta is the parameter, here t is the parameter, here theta is the parameter. Similarly use this x, y, here also here t is the parameter, dy by dx, okay, dx by dt is 2at, for this dy by dt is 2a, then you divide by the, you will get this, okay, then find. It may be noted here that dy by dx is expressed in terms of parameter only without directly involving the main variable x and y, okay, without so in terms of parameter only, may be noted that dy by dx is expressed in terms of parameter only. So this is the example, x power this, y power this, a power time, let x, y, okay, then this is the thing. Second order and derivative means in one more time you have to do differentiation. F of x after differentiation f dash of x, then one more differentiation f double, that is d square y by dx square. Differentiate again, we will get the second order derivative, that is f double dash here. So you can differentiate f of x, f dash of x and f double dash of x. Mean value theorem. Royal theorem. Let function a be continuous a and b and differentiable on a b such that a, okay, where a and b are the real number, there exists some c in a b such that f of c equal to 0. Okay, c is this point where the f dash of c is 0 here, okay, slope 0 here at these points. In each graph the slope becomes 0 at least at one point, here slope 0, here 0, here 0. Euler's theorem as the slope of the tangent at any point of the graph y f of x is nothing but the derivative of f of x at that point, okay. Slope is nothing but the derivative. Mean value theorem, MET, okay, there is such that, okay, satisfy this formula. So now how to use this theorem here in a practical example, okay. Verify Euler's theorem for the function, this function a equal to minus 2, b equal to 2. The function y equal to this is continuous, okay, and differentiable. if you assign minus 2, then minus 2 square is 4, 4 plus 2 is 6. If you assign 2 also, then also it will become 2, 6. F of minus 2 and f of 2 both are 6, hence the value of f of x minus 2 is coincide, that is both are same. Rolle's theorem states that there is a point C in this interval at which f dash of c is 0, that is f dash of c, that is this derivative of this function at this point is 0. So here f dash is 2x, f dash is 2x, at that c equal to 0, here at that point only it will be 0. 2 into 0 0, for other points this will not be 0. Okay, that sense of function. Okay, there exists a point c in this interval at which this derivative of that point is 0. 0 in the derivative, okay, not in this function. This is a derivative of this function, we have to put that point. So here c is 0. So mean value theorem for the function, okay, in this interval. So now use the formula f of 2, f of 4, 16. Okay, 16 minus 4 equal to 6. MET says that there is a point C within this range such that f dash of C is 6. Okay, what is that point here? So f dash of x here is 2x. Okay, 2x, when x equal to 3, then this value will become 6. So that 3 lies in between 2 and 4. Okay, that is the what MET. Okay, you can go through these miscellaneous problems also. So here again important, you should read the summary. So summary, you read what is continuous, what are the rules for continuity, differentiation, this theorem, MET and the Rolle's theorem. Okay.